All right, so I'll talk to you today about some of the work that we're doing on offline batch reinforcement learning. I always like having a sense from speakers about what their labs are really interested and focused on. In my lab, I'm really curious about the question of how can an intelligent agent learn from limited amounts of data to robustly make good decisions. I think this is really a cornerstone of artificial intelligence. If we want to be able to achieve general artificial intelligence, we need to have agents that can both perceive and make decisions. But the other reason that why I think this is a really interesting question is because there's so many places where I believe data-driven decision-making could yield better outcomes for society and people. And so some of the work that we've done has been inspired by the type of application areas that we look at, including in education, like intelligent tutoring systems, and healthcare. And the setting that I'd like to talk about today is counterfactual or batch or offline reinforcement learning. And throughout today, I'm mostly going to be talking about things within the context of Markov decision processes or in stochastic decision processes. So I'm going to be, just for notation wise, I'm going to be assuming that we're in a scenario where we have some sort of agent or algorithm that is making decisions, which involves taking actions, maybe from a finite set, maybe from a changing set, and that impacts something about the state of the world. So the state of the world could be, or it could be, where a robot is in an environment. And then we get back some sort of outcome signal, like a reward observation and some information about the next state. And then one of the critical challenges here is to think about what the policy should be. And the policy here is going to be a mapping from the state of the world to what to do. And in the counterfactual or batch reinforcement learning case, we're going to be in the scenario where we already have data. We already have access to end trajectories, where those were gathered by some either known or unknown policy. So let me just give a couple examples of this.
So question before, so two questions. One was the assumption is the state is fully observed by your algorithm and by the agent. And the second one was the policy is, the exploration policy is fixed, or is it a different policy perhaps for each trajectory?
Great questions. Depending on the setting, we will observe that the state is either fully observed or not. And for the policy like PI-B, we'll call that the behavior policy, sometimes that will be known and sometimes not. So for example, if that is generated by, say, a reinforcement learning agent that is making decisions for customers, we will often know exactly what the probability is of taking each action in this state, and we can log those. But if this comes from healthcare data, those decisions are being made by a physician. What probability do they prescribe aspirin versus, say, Tylenol? So I'll try to be specific about which scenario we're in, and absolutely just ask me questions if it's not clear. Thanks. So I just want to give sort of an examples of where this type of scenario might arise. And another way to sort of call this is kind of what if reasoning. So imagine we're in the case where we have healthcare data, and so we have a series of different patients, and we can look in our electronic record systems and sequence of treatments or decisions that were made for those patients, as well as some sort of outcomes. And the question is, given this historical data, what should we do for a new individual? And so I'll just pause for a second and ask what you might do in this scenario. So like, given the data that you've observed, and let's assume that higher outcomes are better, what might you do in this scenario? Feel free to just put that in the chat, or either is fine. Or what additional questions would you want to ask me before deciding what's the right thing to do for a new individual?
And I guess you'd see if your data is someone who corresponds to this individual or close enough, and then maybe try something that you tried for that person. Maybe.
Yeah, so I think one idea you're saying is like, let's see for that new individual if there's some covariate, make them look like some covariates in the existing data set. So for example, let's say they look both like the middle individual, the guy, and then the one below them. Between those, which would you, okay, yeah, so one person said I'd like a lot more data. Yeah, or a lot more data would be great. Another is, so to think explicitly about our uncertainty over these outcomes, to think about which which outcomes look higher or lower. Though I will say in the context, people often ask me, is the outcome actually well correlated with the decisions that are being made, which is an important question, and is it really what we want to optimize? I also want to just highlight that in this case that we have this critical challenge that the data is fundamentally censored. So we can't see what would have happened for a particular individual, which we can think of as just sort of an initial starting state distribution, if we were to have made a different series of decisions. And so just as a contrast for any of those that are who are primarily working in supervised machine learning, this is one of the key distinctions, is that we don't know what would have happened. We don't have full label information. And so we only get to observe the results of the decisions that were actually taken. One of the other things I want to highlight here is that we also would really like to be able to do some form of generalization as we start to think about the sort of combinatorics of the decisions made and the outcomes. We would like to ideally be able to extrapolate or the types of policies that were from the types of policies and decisions that were made to decisions that might be even better for the future. Now, I just want to highlight in this case that I think this is sort of really at the intersection of kind of causal or counterfactual reasoning and machine learning. And there's been growing interest and excitement over this area, particularly even in the predictive modeling case when we want to be able to make more robust estimation. And there's a really deep sort of things like statistics and econometrics and epidemiology and public health. But the majority of this work is focused on sort of a single decision kind of bandit, often binary setting. So looking at things like treatment effect estimation, where we just have two different decisions and we'd like to be able to estimate which of those is best and maybe which of those is best for which individuals. But I just want to highlight that when we move over to the sequential setting, there's a lot of additional complications. So I really like this figure from my colleagues, David Sontag and Pelez's group with Omar Gottsman and a number of wonderful people, which we're looking at offline reinforcement learning for healthcare settings. And they have this nice graph where they just sort of highlight how one of the challenges in the sequential setting is that if we want to think about taking different policies in the future, that by definition, those different policies, those policies that are different than the way we gathered our data before, are going to result in different actions in some of the same states. And because we have actions that are taken affect the states, then that can yield different state distributions. And so just to give a little example of this here, they think of a case where you start off and you have a whole bunch of patients, and maybe there's some variability in the decisions that were made for those individuals. So there may not always be best practices of care, or there may be sort of openness in some of those treatment choices. And so maybe in this case, different patients did have slightly different care taken at different stages, and we're interested in a particular decision policy, but to have decisions made that match the policy we're interested in. So for example, looking at the very first case, you might imagine that based on the particular oxygen intake, maybe our policy would say, let's do mechanical ventilation, but only some patients got mechanical ventilation. So we sort of lose part of our effective sample size. And then imagine that some of those people are in discomfort, and so our policy would use sedation. And so then again, you can see that as we make this sequence of that sort of the effective cohort of people that received the decisions that are matching our policy of interest make it smaller and smaller. And there's different ways to try to address this, but they often require making different sorts of assumptions about the underlying domain. So what I'm going to talk about for the rest of today is sort of some different ways we've been thinking about this. I think it's there's a lot of really interesting challenges in the offline sort of reinforcement learning setting of what can we do with this historical data, under what assumptions, and what can we say with what assurances. And one of the important things here is sort of how do we estimate the value of a policy from batch data? So this is the scenario where we know we have sort of some particular alternative decision policy we're interested in. And what we would like to be able to do is to evaluate how good it is. So here, my notation is going to be that I'm assuming we have a fixed data set D of past trajectories. We have some policy curious about, we have some initial set of states, and then we want to get this estimate. So policy evaluation is often important within itself, but it's also often important because it can be part of a subroutine to trying to do policy learning. So the second question is sort of policy optimization, which is we don't care just about evaluating one single decision policy, but we care about actually trying to find a good policy for the future. And I want to start by talking about one way that we've thought about doing this, and then I'll talk about sort of both some policy evaluation questions and policy optimization questions, focusing on the optimization. So one of the things that we started thinking about a few years ago is how do we've done some work on policy evaluation before, but most of those were really in service of trying to do this policy optimization. And in particular, we were curious about how we could build on perhaps the most popular form of reinforcement learning today, which is, and think about using those in the offline setting. So if we think about sort of a Markov decision process, and so in this domain, I'm going to assume for now that we are in a Markov decision process. We do get to observe the state, and the state really is a true reflection of reality, and the state is Markov. So if we think of a Markov decision process, we can think of sort of what is the distribution over states and what is the discounted distribution over states. Particular decision policy pi, what would be the frequency for which we would visit the states in the domain by following that policy? In normal policy gradients, we often are thinking about the case where we are acting online, we're getting data from a current policy, and we're computing a gradient of the value function sort of with respect to that policy, so that over time, we're hoping that we will converge to a good policy in that space. Now, most gradient algorithms do not guarantee global convergence to the optimal, but they do guarantee convergence to a local optima. And empirically, that's often very good. So if we look at sort of the kind of the seminal result of like policy gradients, we can see that the assumption is that the data that we have is being gathered from a particular policy. And what we would like to really do is think about, well, what would happen if we want to do this in the offline setting, where we have access to historical data. And so we still want to do policy gradient, but we don't actually get to gather any more data. So we want to be able to sort of do an off policy gradient update. And there'd been some prior work thinking about how you could do off policy actor critic and do off policy gradient approaches, not necessarily for the fully offline case, but also as a way to improve data efficiency. But that work had ignored the bias of the gradient estimates. So it would use data that was gathered from a different decision policy, and then still do this gradient updates. But what we wanted to note is that if you are really trying to do this in the fully offline case, the distribution of states you would visit really could be very different than the distribution of states that you have under your behavior policy. And so this mismatch or this bias could be very large. What we propose to, what you could do in this case instead is to actually incorporate sort of pathwise importance sampling, which is that we're going to correct for the distribution mismatch between the data that we have and the data that we would get under, say, a new policy that we would like to execute. Now, I just want to highlight here one thing that was interesting to us, which is this really becomes an issue and when we have function approximation. If you're in the case where you can perfectly represent your value function and you're in the tabular setting, then this is less of a concern. But when we're dealing with continuous state spaces or very large state spaces, where we need to have function approximation, this can be a big issue. So one thing you could do is you could use importance sampling, which is this really beautiful idea of how do we correct for, how can we use data gathered from one distribution and try to look like an alternative distribution we're more interested in. So in our case, what we'd like to be able to do is to transform the data that we have under our behavior policy to make it look like the data that we would get under our desired target policy. And what we can do here is do that by sort of a product of the difference between the probability of observing a trajectory under our behavior policy versus the probability of observing that trajectory under our target policy. And just as a refresher or for those of you who might not have seen this before, one of the really elegant things about this is that normally the probability of a trajectory depends both on the policy choices made and the underlying domain, the actual transition model. the lovely thing in importance sampling is that because that dynamics model, which is unknown, is the same whether you're in this desired target policy or behavior policy, it cancels. So we don't have to know what the dynamics of the world is. We can do this regardless. So that's one of these really sort of nice, elegant insights for importance sampling for the reinforcement learning case. So then what we thought about is like, well, how could we do better than this? One of the problems with this sort of approach is that in general, if you do importance sampling to correct for this distribution, one of the challenges in sequential settings is that in general, the variance can grow exponentially with the number of time steps or the horizon of the problem. That before, and others have also observed this. And so that can start to be intractable. And one of the observations from other colleagues over the last few years has been, if we really are in a Markov setting, which we're not always, but if we're willing to make that assumption, then we may not need to think about this sort of full product of overall time steps of this ratio of the probability of decision made over the target divided by the behavior. But we can instead think about how would be the stationary distribution of states and actions taken under our target policy versus our behavior policy. And so various people had started thinking about this and thinking about the sort of stationary distribution ratio, thinking about the fact that instead of trying to think about this product that's going for the number of time steps, that we can instead just think about how does the stationary distribution change between our behavior policy and our target policy. We're really leveraging the fact that the system is Markov. So what we pointed out is that we could use this also for policy optimization. So we can get sort of an unbiased estimate of the policy gradient by doing this state-wise importance sampling. So we don't have to do this full trajectory level, but we could do it over just the stationary distribution. I see there's a question.
I have a quick question. So when you say behavior policy, are you assuming all the data is collected using a single policy that you don't know, or can there be multiple policies the data is coming from as well?
That's a great question. In the general, in the in this case, like where we have the sort of the full trajectory, it's fine as long as we know what the behavior policy is. We can correct for this. In the stationary distributions, I think it's a little bit more subtle. We would sort of want to know which behavior policy. You could just sort of take an average over all of them, but for theory and correctness, you would want to know like which trajectories were generated under which behavior policy. And so then you can imagine getting different ratios for each of the different behavior policies and then combining across those when you're getting your estimate.
Okay, thank you.
Sure. So the benefit is that we may be able to have a much lower variance estimate of the policy gradient. So now we are leveraging our Markov assumption and then getting this reweighing of the data based on what would be the distribution of states we'd get under the target policy compared to the behavior policy. And so this is what we proposed for our off policy gradient theorem. And we produced an algorithm that could leverage this. And so we're using this during the policy approach. And again, I'll just emphasize here that this is all done on sort of a single set of data. So we're just going over, we're not gathering any more data. We're just going over our data over and over again and doing policy gradients in a way that corrects for this sort of distribution mismatch. So when is this a good thing to do and how does it work? Well, what we're sort of thinking about is the case that we are thinking about the scenario where we have some states that are visited by our current policy. Think of there as being sort of some states that are actually visited under the current policy that we gather data for. And we don't want to go outside of that, because if we go outside of that, then we're going to be starting to have very little support for the decisions that are made for other states. Or another way to say that, I think, is that our uncertainty should be very high if we start to visit states and actions for which we never would have visited, or we have extremely low probability of visiting them under our behavior policy. If our doctor never prescribes aspirin for a headache, we cannot evaluate a policy in which someone prescribes aspirin for a headache. And when I say it like that, it sounds sort of obvious. We can't we can't evaluate what would happen for decisions that were never made in certain states. But this, I think, because of the way that we often do function approximation, it can often be less obvious exactly where one can start to run into trouble in terms of this uncertainty and essentially over to parts of the decision space for which we have very little empirical support. So in this case, and in some of the other work I'm going to talk about today, we tried to be more explicit about that, of saying like, look, we really need to sort of stay within the state actions space for which we have good support and we have sufficient sort of empirical data so that we can learn a policy that we think will work well. And so what we wanted to have in this case is to sort of, if it was the case, exists a really good policy that visits states and actions that are covered within your behavior set, we would like to be able to recover that, because we do have support then for the types of states and actions that we would visit under pi star. And so that's in some ways sort of the best we could hope for, is that we could hope to get like a policy that's really good within the support that we have. And so what our assumption is that there's at least one optimal policy that is covered by the behavior policy. So that is our assumption for our theory, is that there does exist a good policy.
There's a question on the chat, actually, Emma. Sorry.
Yes. So there's the question is there a quantification for how off we can go from the policy available in the data set? Good question. I'll tell you what we assumed here. Here we assume that we're only going to try to compete with the best, that we're going to assume that the data does cover at least one pi star. And later I'll come back to your question and say like, we'll be more sort of how far we can go. So great question. And if I don't answer it later, just remind me, but I think that'll be addressed by the second part. So here we're thinking about this policy gradient case where we make this assumption that we did cover a good policy. And so then under that assumption, we give the first convergence result for off policy batch policy gradient, which is, we are assuming that the system's a Markov decision process. We're assuming we have coverage of an optimal policy. And we can get sort of the error of the state distribution ratio and the critic going to zero, and that the second moment is bounded. And then given that, we will converge to a stationary point of the policy value. Now, I just want to be transparent here that we're not giving a global convergence guarantee, but neither do policy gradient. So we're saying that we are guaranteed to converge, which prior work was not, under these settings to sort of a stationary point, which in some ways is quite the online policy gradient approach. So let me just say a little bit about.
Just a quick question before you. So how easy is it to sort of verify any of these? I mean, I guess the coverage of optimality is probably impossible to verify in some sense, right? Yeah.
Coverage of optimality, I think, is impossible to verify, unless, not necessarily. I think if you have a behavior policy that is random, then that has to be true. So if you know something about your behavior and you know you have sufficient data that you essentially are going to visit any reachable state action pair, then I think then by definition your behavior policy has to cover. I think the harder case is if you know you have very little data or your behavior policy is much more restricted, then I think verifying one is very hard.
Or you're in continuous state spaces, in which case even if you have a fully random, I mean, in the sense, whatever distribution you have, you still have this trouble, right?
Yeah, then I think the best you could hope, like if you essentially discretize the space and you'll get something to sort of epsilon optimality under that sort of discretized representation.
Okay. Thank you.
Sure. All right, so let's see, let me say briefly how this works in simulation, again, with a fixed data set. And I just keep emphasizing that because often in reinforcement learning, we talk about policy learning. Q-learning, which is one of the most popular reinforcement learning algorithms, is an off policy learning algorithm, but it's not normally just for batch data. So I'm talking about right now, we're gonna not have any more data. So what we want to look at in this,
the chat, actually, just before.
Yeah. Your optimal policy is covered. Does the theory still work? I think that would be easy to adjust to. I think the theory could be extended to that case. We didn't consider it, but it's a good question. I think that would be, I don't think that would be hard to include if you have like a near optimal policy. Now, get to that policy. Like even if there is an optimal policy, we're just getting a local convergence result. So I think that this would be pretty reasonable to try to achieve. Good question. So what I want to emphasize in this case is that we're trying to look at a setting where like the behavior policy itself is not that great. It might have decent coverage, but its actual performance is not that good. The reason I want to emphasize this is that I think another dominant paradigm right now in reinforcement learning is imitation learning, where we're just trying to imitate the previous data we have. And I think in some cases, like where we have expert data, say from a surgeon or, maybe an expert helicopter flight attendant or flight controller, that could be really good. But what we're really interested in is the case where we hope to do much better with the existing data than was already possible. And so we wanted to see whether that's the case, that really, we can take the same data and use that to learn a decision policy. So in this case, what you can see here is blue is behavior. So this is the actual performance of the behavior. And then on the x-axis is the number of policy gradient steps. So again, no new data. This is just sort of our algorithm running and it's trying to learn a new policy. And we compare it to sort of off-pack, which only corrects for the action, not the distribution and state mismatch. And then we also looked at SAC and ACER, which was not originally designed for the batch setting, but can be adjusted to that. See that even just sort of correcting for the action mismatch, you already can find something that can do much better than the behavior policy. So it's certainly possible to learn something much better. But excuse me, with our approach, you could do much better than that still. So that indicates that accounting for the fact that you're going to have this state distribution mismatch as well as action is important. And you can see here too that this performance, I think in this case 200 is optimal. So with this data, you even though the data was gathered under something highly suboptimal. And I'll just emphasize here that some of the other methods that have been tried before that can be adjusted to the setting that don't explicitly try to do this accounting for the state distribution mismatch do much worse than we do. Okay. And we can see this too in some other domains too. So this is an HIV treatment simulator. And in this case too, the behavior policy is pretty bad. We can do better by some of the others, and our approach that corrects for the difference in states does much better. So just to summarize that part, this was sort of the first convergence result for non-tabular off policy gradient. And by correcting for the state distribution mismatch, that was really beneficial in terms of actual empirical performance. Now, this result is basically sort of, kind of a first step where it was looking at this left-hand side of saying, how do we get a good policy? But that we got out only had this sort of somewhat weak convergence guarantees. So that's a good first step, but we'd like to do much better. And in particular, I think it would be really lovely to have something that's equivalent to kind of structural risk minimization for batch reinforcement learning, meaning that we can select policies for which we have good generalization guarantees on their future performance. And so in particular, we would expect to have something that might look like the following, where we can select a policy which has that should hopefully depend something like the complexity of the hypothesis classes that we're considering, as well as something about how big our data set is. So that's sort of something that I would love to see for us to have sort of generalization guarantees on the policies we would get from historical data. I would like these sort of bounds to be able to, account for finite samples, be suitable for continuous and vectored state spaces, think about the expressivity, and ideally make minimal the underlying stochastic decision process. The other thing I would really love is just practical approaches, sort of the equivalent of cross-validation for reinforcement learning. And again, I think that our lab is there's been a lot of great students and making great progress on this, and a lot of other labs have been thinking about this too. I don't think we're there yet, but I suspect over the next 5 years, there's going to be, I'm hoping we're going to really get to the case where there's sort of practical tools that can be deployed in a much wider set of industries. And I think that's a reasonable thing to hope for. Again, I'll just say in this case, there's a lot of subtleties to doing cross-validation here, including the fact that in order for us to do off policy evaluation, we have to have pretty large test sets, and we can't do things like leave one out cross-validation because the data that we have has to be sufficient to evaluate the value of a policy. So I'll just say a little bit, I think this area has been greatly expanding over the last 5 years, which is really exciting to see. And I think there can be differences in the different types of assumptions people are making, or the different types of evaluation criteria that people are hoping for. So I think it's helpful, just before the next things that I talk about, to talk a little bit more about, what might we hope for in these settings. So in particular, I think it's useful to be explicit about some common assumptions. So one is that the process itself is stationary, so that we're going to deploy, excuse me, in the same decision processes where we get. I think that this historically was a pretty reasonable assumption in certain cases, but I now have several students thinking about this in other settings, say like in healthcare. COVID certainly has changed the distribution of people coming in, say, to the intensive care unit. And there's a lot of cases where the domain really isn't stationary. And so thinking about that, thinking of how the dynamics model might change, or the initial states distribution might change. That said, I'm not going to talk more about that today, but if it's something you're interested in, I'm delighted to chat. A second assumption that we have thought quite a lot about is whether the system is Markov. I think in the reinforcement learning community, this is almost always assumed. I think in some of the domains that we're looking at, it's really hard for me to believe that that's true in the features that we have access to. So I think for things like education or modeling people's physiology, often we just don't have access to all the features we need to make the system look Markov. And is sequential ignorability, or no confounding. And this is the assumption that that the decisions that are made depend only on the observables, and that there's not some additional information that are affecting the decisions that are made in your data set. So for example, in the healthcare setting, if you go into the doctor's office and their decision depends both on things that are recorded in the electronic medical record system, and maybe in a conversation, or how you're visually appearing, and that's not in the notes, then that is affecting the decisions that are made. And that can introduce confounding. And I think this is also a really interesting issue. We've done a bit of work on it. Today, we're going to mostly ignore it. But the thing that I'm going to talk more about, and I already started talking a bit about, is overlap, which is the assumption that you have coverage. So the assumption that like your evaluation, distribution of states and actions, that if you were have non-zero probability of visiting a state and action over a target policy, that you also would have had a non-zero chance of visiting that state and action under your behavior policy. And I think that's a really important assumption that we started talking about a bit before, and I think has started to have sort of an explosion of interest over the last couple of years. In terms of evaluation criteria, I think that that's also been really interesting to look at. Some people care a lot about computational efficiency. There's performance accuracy, as well as things like performance bounds, where we can consider sort of how the performance is changing with the amount of data we have. And then there's also these sort of two separate tests of whether we're doing off policy evaluation or actually maximization. Now, I think in terms of where we are so far, there's been a lot of really interesting work on this, including on the theoretical side, trying to quantify some of errors and the value function errors, including some great work by Nan Zhang and his lab, looking at sort of, can we get bounds on the quality of the value function that we return, including in the Markov case. And a lot of these have required quite strong assumptions over, for example, the fact that we can represent the optimal Q function in the class, things like that when we do Bellman backups, here T is a Bellman backup, our dynamic programming backup, we stay within sort of a function class that we're looking at. And then this assumption on the bottom here, which is what I'm going to talk about more in relaxing this, which is that we sort of have very good data coverage. So that we have coverage for sort of perhaps almost all states and actions that we might expect to visit under any policy by the behavior policy. And that's a pretty strong assumption. I think in some cases, like if you have a uniform randomized control trial, true. But if you're using more like business as usual data, this might be very far from true. So I'll just skip it. I think getting these sort of analyses is quite hard. But before I dive into a little bit more on the concentratability, I just want to emphasize that though I'll be talking more about some of our theoretical results for this, I do want to highlight that I think this is important, not just in theory, and actually not just for sort of offline only settings, but it's also important for deep reinforcement learning. And there was this really nice work by Scott and Doina and others illustrating that because a lot of online reinforcement learning also relies on doing this sort of off-policy evaluation, that this really can make a very big difference. Their method is BCQ, which is one thing that tries to account for some of this data distribution mismatch. So again, the challenge here is this overlap requirement that we need to, if say this is the policy we calculate, then the data must have been gathered in a way that tries out all the actions that has no non-zero probability. And again, that if we don't cover that, then we just can't evaluate that policy. And that sometimes it can be really hard for us to know whether that's true. So we have some recent work that came out last year at NeurIPS, which I sort of talk about as like doing the best with what we've got. And it's really a pessimism approach, and it's trying to do a whole optimization without full data coverage. And I just want to highlight that when we were developing this work, and it's going to be a model-free method that is suitable for Markov domains, and it's going to be a pessimism approach. I think this was really an idea that sort of ripe for its time, because I think that a number of different labs all simultaneously started thinking a lot about being precise about our uncertainty given historical data, and then how we can create policies that are robust to that. I think there were 3 or 4 concurrent NeurIPS papers that all have sort of very similar ideas around pessimism. And then since there's actually been a flurry of work that sort of continued to investigate the theoretical limits and other approaches to sort of doing this kind of pessimism and working within the data that's available, as opposed to assuming that we have really good data coverage. So that's just a highlight of sort of where we're going and what's happened since. But let me just say sort of the main idea, which is when we do a policy, we're going to restrict the policies we consider to those that actually have overlap in the data. And our insights were that we wanted to do that. We wanted to make it computationally tractable, and we want to be really precise about our uncertainty. I'll just highlight that sort of up to that point, there'd been a lot of interest, but together with my student Yalu and our great colleagues over at MSR, we constructed a couple really small examples to illustrate why some of these previous approaches didn't work. I don't think I have time right now to step through the examples carefully, but I'm happy to talk about them offline. But what you can see here is, so on the x-axis is the amount of data. This is like a really simple sort of small finite state MDP. It's kind of like a chain. And what you can see here is that a lot of the previous approaches up to that point had this sort of concerning performance, in that you would expect when we don't have a lot of data that some of these methods are going to end up having worse policy. But you would sort of hope you have some kind of monotonic performance, so that as you get more and more data, we consistently get a policy that's better and better. What you can see here is the green line is ours. So sort of across the range of these different data set sizes, we do well. But a number of these other approaches had this sort of slightly concerning behavior where like they'd start off actually doing pretty well. And as they got more data from the behavior policy, they actually would do worse and kind of get misled and find less good performing. And then later, and as more and more data is obtained, they would sort of go back to finding a good policy. And the reason for this is that a lot of the previous approaches sort of mostly focused on trying to correct or trying to think about the difference in the actions that are taken given a certain state between the behavior policy and the target policy. And our insight here, similar to the insight that I just mentioned before in the previous pair, is that we really have to think about the well, that because the actions under different policies, we're going to visit different states with different frequencies, we need to not just think about sort of conditional uncertainty once you reach a state, but thinking about how much support we have for those states. And so because of that, you can get this sort of strange behavior where if you have rare states that you don't visit much, at the beginning, you might never visit them and you sort of don't get, the algorithm doesn't get confused that you might have high performance there. But as you get more data and you occasionally, the algorithm can get misled because it doesn't take into account that those states are very unlikely or very rarely visited, and we just don't have a good way to quantify the performance yet. And this is true also for some other algorithms, even that actually sort of regularize back to the behavior policy. And in some ways for a similar reason, in that if you have very little data, let's say even under your behavior policy, you may have an inaccurate estimate of your behavior policy. Don't have very much data to evaluate it. And so they're regularizing or going back to what you might think is good under your behavior policy, or leveraging behavior policy estimates might also mislead performance. So we sort of looked at this and saw these other methods that are just not thinking, that are not directly representing the uncertainty due to the fact that we just have limited, say, visitations to certain states or of support in those, can lead to misestimation and misoptimization when we're trying to optimize over the space. And so our idea is really quite simple, which is just like how often in reinforcement learning, we think about being precise about our uncertainty and being optimistic with respect to it when we do exploration. Here, we want to be explicit about our uncertainty and be conservative or pessimistic for parts of the state action space where we have limited data. And so essentially what we want to think about is, if we don't have much support for a state action, for part of the state action space under our behavior policy, so for example, say our density is very small there, then we may want to use a pessimistic estimate of what would be the value if we reach those states and actions. So in particular, we can set these thresholds to account for statistical uncertainty due to finite samples. So we have sort of it's a very small change. We just our Bellman operator to include this filtration. So if you have enough support for a state in action, then we're going to plug in sort of our new normal like value function approximator for the expected discounted sum of future awards for the next state. But if you don't have enough support for those next states, then that filtration function is going to evaluate to 0. And so assuming your rewards are bounded by 0, that's a pessimistic estimate of what it would be like if you reach those states. And so since we're incorporating that in the Bellman operator, when we do backups, we will get something that's conservative. And we can do this either for sort of like a Bellman operator, we're trying to extract, do sort of value function iteration, or if we're doing sort of a policy evaluation. And so again, it's a sort of simple idea of saying like, we're just going to be conservative. If we don't have, then we're going to assume the value of those states and actions is 0. And we call this marginalized behavior supported policy optimization. So just to contrast that, because I think one of the primary, well, I think it was a useful idea to think about pessimism, but I also think compared to some of the other work that was concurrent, I think one of the primary benefits of our approach is also that we have some nice theory in this case. And I think compared to prior theory, which sort of had to assume that your behavior policy covered everything, and then you would compare the resulting pi that you get from that algorithm to B star and show that it was close. What we said instead is, we're just going to sort of implicitly think of there being a policy class which is covered by the data you have. So you have some data, and that sort of provides support for evaluating a number of different policies. And we want to compete with the best policy in that class. And that's sort of maybe the best you could do, is that, you know, again, if the doctor never prescribes Tylenol, then you never will know what that's like, but we can hopefully figure out a policy that is good within the support of the data. And again, we don't explicitly construct this policy class, but our algorithm is only sort of trying to compete with it. And so then we make several key assumptions. One is that we have bounded densities. A second is that we have bounded density error. So we're really dealing with the continuous state and action space case here. And I just want to note that I think this to us introduced a number of different subtleties, because in the tabular setting, you don't have to worry about densities that could be greater than 1. But in some of the steps of our theory, when we change between the distribution under the behavior policy to the distribution under the target policy, we have to think about sort of that reweighing of those states and actions. And so these sort of continuous densities be accounted for. And so what we assume is that we can have access to an estimator of our behavior policy that has bounded error under the total variation, and that our bounded, our densities themselves are bounded. So we don't sort of go to a state that is a delta function and stay there forever. There's not sort of a funnel state. And then we assume completeness, and then pi completeness. 3 and 4 are quite standard in a lot of the off-policy learning. And again, all of this is assuming that the system is actually Markov. And then we can get a theoretical result that allows us to say how good is the policy that we get by doing this sort of pessimistic policy iteration or pessimistic value iteration compared to the best policy within the supported set. And so what you can see here is it's getting closer to that type of structural risk minimization I talked about before, in that we think about sort of how big is the function approximator class we're thinking of, the policy class, with what probability do we want this to hold. And then we see here that we have this B term, which has to do with the thresholding. And so this sort of gives us a way to quantify how good is the resulting policy that we'll get given some amount of data and given the particular function approximators that we're using. So empirically, we can also find that in this study, this is Hopper, another sort of control task, much better solutions with the same data. And I think, to me, again, this is something that makes me particularly optimistic about offline policy learning, is that I think that, of course, this is a simulated setting, but I think that there can often be cases where there is variability in the data, and we've seen this before in some of our education work, which allows us to, which if we leverage it and we sort of do this kind of policy mining, that we can find solutions and policies to deploy in the future that are much better than existing policies are. And so what you can see in this case is, again, that our approach is doing much better than the previous approaches, including behavior cloning. Now, I just want to briefly say that there was some prior work that sort of, I think there's sort of a nice, interesting ongoing debate about is model free or model based better. And there'd been some interesting work to suggest that there could be some nice theoretical cases in general in RL that models might be better. There was this parallel work mostly focused on model-based RL. So I think at least 3 of ours all appeared at NeurIPS at the same time. And they took sort of a similar approach in terms of trying to be explicit about our model uncertainty and got some really nice performance on D4RL, which is a benchmark set of tasks. But a lot of them didn't develop sort of these finite sample function approximation bounds. So after work, we did some early comparison. And I think this sort of was really more about, is it model free or model based? And what we could see is that our approach, so MOPO is one of these sort of concurrent approaches. And I think it varied by the type of task. So in some tasks, our approaches, our MBS did much better than MOPO. In some other tasks, were either comparable or worse. So I think the jury's still a little bit out, but there's been a lot of performance. So just to summarize, I think that this and the previous work that I mentioned is really going into this sort of pessimism under uncertainty and allowing us to handle the fact that we want to leverage the existing data we have and try to find policies that are better, supported by the data that's available. And that by having explicit representations of our uncertainty, we can leverage that within our algorithm to get more robust estimates and sort of try to compute policies that are robust with respect to pessimistic sort of instantiations of our uncertainty induced by the sort of statistical limitation of the amount of data we have access to. And again, I just want to emphasize there's been a lot of really great follow-up work on sort of pessimism under uncertainty for this offline case, and also better trying to characterize like when is pessimism the best approach and what forms of, how do we have good representations of our uncertainty. So I think rather than
quick question, could you just what was the policy class that you were comparing against? Could I just have a look at it? I'm still trying to understand that a little bit. Sorry.
Yeah, no, that's a great question. So I think in the past, the results were mostly for the best policy in the set. So V star, assuming that your value function classes can realize value function. And so then the prior results would say, our algorithm's going to get you something close to the optimal policy, but your data has to cover not just that optimal policy, but actually any policy that's realizable in your MDP. And it's sort of expressed through this ratio here, which says that your state action distribution has to have sufficient support for any alternative state action distribution you might get under any policy, even if it's not. And what we said instead is that we are going to try to compete with all policies that have pretty good support. So like for which μSA is sort of greater than a threshold. And so if our optimal or one of our optimal policies is in that set, then we're going to be competing with pi star. But if it's not, then we're going to be competing with whatever is sort of the best policy that is well supported in metadata. So if I think of there being distribution of states and actions that can be visited by the behavior policy, as long as that's a sufficient probability, then I will try to compete with the best policy that would also visit those types of states and actions.
So maybe just a question based on that. I was actually asking based on Ben's question from the beginning. Suppose I have this data and I want to go out and get more data. It doesn't tell me where I should go for more data, does it? Or can I use this to tell you which states I should explore more to get more data?
I think that's a great question. So this does not say where you should explore. This is just for the offline case. It doesn't consider the setting where you have existing data and then you want to explore a little bit more. In some other work that I'm not going to talk about today, we've been thinking about that case of where you might have like a budget of exploration and including like, what if you have some data already, where should you explore next? So I think, but this is not tackling the sort of, you've got some data, how should you explore next?
Thank you.
So just in the interest of time, I'm not going to go through all the rest of the work. I just will say sort of briefly what a couple of other things that we've been thinking about. So one thing that I think is a really interesting case that my student Jonathan and together with some colleagues we're starting to think about has been, how do we guarantee the best in class policy? So those previous results I talked about still assume the world is Markov, and they also assume often that you've got like a value function that's pretty good. In the second case, and in the first case, we were just getting sort of local convergence results. I think in many cases, we just don't know if the system, if the modeling assumptions we make are correct, and if the system is really realizable in those modeling assumptions. And so I think in those cases, we'd like something more agnostic, something more like, can we guarantee that given the function approximators we're using, either for the value function or the models or the policy, that we're going to be able to extract the best policy in that class. And so I'll just say briefly that like that we have some results on that. So together with Xinquan Ni and Stefan Wager, we have a paper in JASA doing this for a particular type of decision policies. So this was where you might be making medical treatments or others where you sort of have data and you want to decide when to stop a process and what decision to make when you stop. And so we have, to my knowledge, the first guarantees on performance of the best policy you choose in the class in this setting. So I think that was really exciting, but it only worked with sort of a finite set of decision policies, which wasn't too bad in this setting. But I think in general cases, it's still very open about how to do this. Like, how can we sort of get away from some of these modeling and instead get results that are more agnostic to those and that don't necessarily have to make as strong Markov assumptions. And then I'll skip ahead for a second and then say the other thing that we've thought about too is sort of thinking about what if we want to do this in practice, and can we do, how would we pick across different policies, particularly if we don't want to make Markov assumptions. And so I had the pleasure of collaborating with my postdoc and a number of other people on some work where we at sort of trying to make guarantees on the performance of a policy before we deploy it. And so we sort of want to have these high probability constraints and also thinking about going beyond expected performance, but where we might have additional objectives that we want to consider. So I won't go through that now, but I'm happy to talk about it. I think that's another really exciting area of like, how do we have reinforcement learning algorithms that move beyond expected performance and think about other outcomes. Let me just skip ahead. So I think the work that we've been doing over the last 5 years has really been trying to think about how can we leverage the existing data that we have and better take advantage of that opportunity to provide better decision policies for future use. I think there's us and others have made good steps towards that, and how do we have things like structural risk minimization or cross-validation for RL. But I think there's still a lot of really important open questions in making these both theoretical results that are more general, as well as making these into practical, say, small nonprofits could use in order to make better decisions in terms of some of their operations. So if anybody is working on this or is interested, I'm delighted to talk more. Thanks.
Thank you, Emma. And maybe I'll open up for questions if there are any more.
Yes, hi. I'm really curious. Does oppose still work under the confounded setting?
Do these work under the confounding setting? Is that the question?
Yes, the opposed policy gradient algorithm. Does that still work under the confounded setting?
Great question. No, I don't think it would, because it's making the Markov assumption and assuming the state action distribution we have. The states really are Markov in that, and that then we can get the ratio. And if it's if we have confounding and if decisions are being made under different distributions, I don't think that will hold. It's a great question, but I don't think it will. We have another paper where we provide some results for the confounding case under some limited assumptions, but I think it's still a good first step to account. Essentially, it's almost like a sensitivity analysis of saying, if you've got bounded amounts of confounding, can we bound the influence that will have over your off policy evaluation? But in this case, the way that I think about confounding, and others might have other perspectives, is that it can essentially cause our overlap assumptions to be violated. Because if we have state aliasing or sort of confounding, state aliasing due to confounding, it can make it look like we have support under some states and actions, which we don't really. Like maybe doctors never make that decision in those cases. And so we can end up with erroneous estimates.
That makes a lot of sense. Thank you so much.
Thank you. There was something else in chat.
Yeah, great question. So that was one thing that I was trying to sort of emphasize. I'm happy to go back because a lot of slides, but that was one thing I was trying. I'm optimistic that we can do better than imitation learning, and which is, I think, of sort of this example of saying, what if we just sort of took what if we took supervised learning? So you can see in this case, what we have is the blue is the behavior data, and you could have, and that's the actual performance of the behavior data we have. So supervised learning, if it just tried to imitate the behavior policy, would do pretty badly, like around 20 in this case. But the nice thing is that this behavior policy covers some policies that work really well. And so you can see in this case, like our algorithm, which is green, does much, much better. And again, really because like it could be that in your behavior policy, sometimes you take really good actions and sometimes you don't. Maybe you have a mix of like extremely expert doctors and like some people that are just learning. And so we're sort of trying to learn to do as best as the best sort of people that are making best people or best agents that are making the decisions. And so we're only sort of constraining ourselves to be within that set, but we're trying to sort of say, let's always find like the best expert for any state in action and then try to find a policy them as opposed to try to match the average.
So I had a quick question. I mean, the setup here is, I mean, I'm just trying to understand. It's like, that you always get a reward in every step. Right?
Good question. We don't have to have the dense reward setting. You could also have just like a reward at the end of, just at the end of a trajectory.
Thank you. Any other questions from anyone? If not, I want to thank Emma for an excellent summary. Thank you.
Thanks, everybody.
Thanks a lot. Bye-bye.